In this video, I'm going to show you how to calculate related rates using similar triangles. So, suppose that Charlie, who is 5 feet tall, stands in front of a streetlight that is 15 feet tall. If Charlie walks towards the light at a speed of 3 feet per second, then how fast does Charlie's shadow shrink? Here we've got a nice diagram of the situation. Here's Charlie is 5 feet tall, and there's the streetlight, which is 15 feet tall. And Charlie is moving towards the streetlight, and that's causing the shadow, this portion here, to shrink. Okay, so now let's jump into the math. What is it that we want to find? Well, we want to find how fast does Charlie's shadow shrink. So we should assign a variable to Charlie's shadow. How about y? So Charlie's shadow is y, and we want to find what is dy dt, the rate of change of y. Okay, but before we jump into that, let's take inventory of what else we know about the problem. We also know that Charlie is walking towards the light at a speed of 3 feet per second. So this distance between Charlie and the light, call it x, that is decreasing at a speed of 3 feet per second. So dx dt, the rate of change of x with respect to time, x is decreasing by 3 feet per second, so dx dt is -3. Okay, cool. So let's jump back to dy dt. We want to compute that, and the way we compute it is, as usual, we want to pull it apart into dy over something times something over dt. Now, what are these somethings? Well, we know dx dt, so that's a strong indication that we should fill in with dx. And if we fill in the top with dx here, we need to fill in the bottom with dx there, so it's like they cancel out. Okay, so we have dx dt, that's just -3, but what is dy dx? Well, we can compute dy dx if we can construct an equation relating y and x together. But where will that equation come from? Well, it'll come from similar triangles. Look at the diagram here. We've got a small triangle here that has sides 5 and y, and a large triangle here that has sides 15 and x plus y. And the key thing here is that these two triangles are similar. They have all the same angles, which means they also have the same ratio of side lengths. So we can say that the ratio of side lengths in the small triangle, the ratio y over 5, is equal to that same ratio in the large triangle. But in the large triangle, instead of just y, we have x plus y. So that's what will go up top here, x plus y, and then that is all over the other side, 15. Great, so now we've got an equation relating x and y, and now let's just go ahead and solve for y in that equation, and then we'll be able to take the derivative dy dx. So to solve for y, why don't we simplify this equation a bit? Let's just multiply by 15 on both sides to cancel out both denominators. So 15 over 5 is 3, so 3y is equal to 15 over 15, that's just 1, cancels out, just x plus y. So we have, subtracting y from both sides, that 2y equals x, and then dividing by 2, y equals 1/2 x. So that means, taking the derivative with respect to x, we get that dy dx is equal to 1/2. And there we go, that's our other quantity that we needed to plug in here. So that'll give us dy dx, and we already had dx dt, so we are home free. dy dt is equal to 1/2 times -3, which is equal to -3/2. Okay, but hold on just a second. The question is asking, how fast does Charlie's shadow shrink? So it's already supposing that the shadow is shrinking. And you wouldn't quite say that it shrinks at the rate of -3/2 feet per second. You would say that it shrinks at the rate of 3/2 feet per second. The word shrinking already takes care of that negative sign. So that will be our final answer. We take away that negative sign because the word shrinking already does that for us. So 3/2, and then our units are in length per time, feet per second. So there we go. That is how fast Charlie's shadow shrinks. Here's our next problem. A trough is being filled with water. The trough is 8 meters long and is in the shape of an upside-down triangular prism, where the cross-sections are isosceles triangles having base and height of 4 meters. Water is poured into the trough at a rate of 6 meters cubed per minute. We want to find out how fast is the water level rising when the water in the trough is 2 meters deep. Okay, so first thing, let's assign a variable to the thing that we want to find. We want to find how fast is the water level rising. So we can go ahead and label in the diagram the water level. That's just the height of the water. So why don't we call that h for height? And our goal is to find dh dt at the moment when the water in the trough is 2 meters deep. So at the moment when the height of the water is equal to 2. So that's what we want to find. But before we jump into that, let's take inventory about what else we know about the problem. Are we given any other rates of change? Well, yes, we're told that water is being poured into the trough at a rate of 6 meters cubed per minute. So that means the rate of change of the volume of the trough with respect to time, that's equal to positive 6. Volume is increasing at a rate of 6 meters cubed per minute. Okay, so now back to our dH dt. We're going to break that up, and one of those parts that we break it up into is going to consist of our known rate of change. So dH d something times d something dt, and the something, of course, will be dv, because we already know what dv dt is. Now the challenge is to find dH dv. So can we get an equation relating h to v? Well, we know that v is the volume of the trough. And the volume of this prism is just equal to the area of our triangular face times the length of the prism, which is 8. Now keep in mind though that this is referring to the volume of water within the prism. So we're not using the full area of the face, we're using only the area of the face that is covered by the water here. So just to be very precise, let's draw that triangle once more, kind of enlarged so that we can see what's going on here. So we've got our triangle here. It's filled up to a particular level with water. That level is given by the height h, and the triangle is a 4 by 4 triangle, height 4 and base 4. And for now, why don't we label the base of the triangle formed by the water as having base b. So this way, the area of the triangular face, that'll be just 1/2 times base b times height. And then that'll be multiplied by 8 to give the volume. So simplifying, we have that the volume is 4 times base times height. But remember, our goal is to find dH dv, so we want an equation with just h and v. Right now we've got an equation with v and h, but also b, and we don't want b in that equation. So how can we get rid of it? Well, again, let's use similar triangles. This shaded triangle here is similar to the larger triangle of the prism. They have the same angles and they have the same ratio of sides. So that means in the smaller triangle, the ratio b to h, that's equal to the same ratio in the large triangle, which is just 4 to 4. So b over h equals 4 over 4. So that means b over h is equal to 1, which means that b is equal to h. So we can just go ahead and sub that in for here. Volume is equal to 4 times b, but b is just h, and then that times h again. So volume is equal to 4h squared. So finally we've got our equation relating volume and height, and we can get the derivative dH dB by differentiating. Since it's already solved for v, why don't we differentiate with respect to height? And that'll give us dV dH, and then we can just take the reciprocal. So doing that, we get that dV dH is equal to the derivative of 4h squared, which would just make 8h. So then taking the reciprocal, dH over dV is equal to 1 over 8h. Now we're interested in at the moment when h equals 2, so we'll compute that here. dH over dV at the moment when h equals 2 is equal to 1 over 8 times 2, which is equal to 1 over 16. So there we go, we've got dH dV, we've got dV dt, we can just plug them in. So 1 over 16, that's going in for dH dV, and then 6 is what's going in for dV dt. So we have that dH dt when h is equal to 2, that's equal to 1/16 times 6. And then 6 divided by 16, we can cancel out a common factor of 2. You get 3 over 8. And what are the units here? Well, the units of length over units of time. Length is meters, time is minutes. So 3/8 of a meter per minute. That's how fast the water level is rising when the water in the trough is 2 meters deep. So now we know how to calculate related rates using similar triangles. And in the future, we'll continue to learn how to calculate related rates in other contexts, such as with trigonometry and with cones.